All right, if we have a look at example 11 specifically, again, two possible methods, so I'll consider both methods. If sine x equals 3/5, well then obviously sine squared x equals 9 on 25, cos squared is 1 minus sine squared. So if I go through that, I'll end up with a cos squared x is equal to 16 on 25. Take a square root of those, I'll end up with cos x is equal to plus or minus 4/5. In the domain that we're interested in, pi on 2 to pi, it's a second quadrant where cosine is negative, so we'll get cos x equals negative 4/5. All right. Tan x, sine x on cos x will also give me negative 3/4. Conversely, method 2, if I know that sine x is 3/5, sine is opposite over hypotenuse, which means from Pythagoras' theorem, the adjacent side must be 4, which leads me then to giving me adjacent over hypotenuse for cos, opposite over adjacent for tan, and then just determining which quadrant I'm in, so whether it has to be positive or negative. All right. All right, let's simplify tan squared x plus 1 over tan squared. Couple of options we could approach it. I actually just chose to identify that tan squared x plus 1 was the same as sec squared x, and then write both of them in terms of sine and cosine. So sec squared is 1 on cos squared, tan squared is sine squared on cos squared. Divide by a fraction, flip it upside down and multiply, which means my cos squareds will cancel. So I get left with a 1 on sine squared x, which is a cosec squared x. Alternatively, I could have done division and got tan squared on tan squared, which is 1 on tan squared, which is the same as 1 plus cot squared, because 1 on tan squared is cot squared, and 1 plus cot squared is cosec squared. All right. So there's a few different ways we could have approached that. Okay, if we continue on there, we can see that cot squared x minus cosec squared, well, cosec squared is 1 plus cot squared. So then if I multiply that negative sign through, I'm going to get cot squared x minus cot squared x, which is 0, and get left with a negative 1. So it actually works out quite nicely. All right, keep moving through. So again, sine 4 to the x. I'll just tidy that up a bit. I thought the easiest way really was to identify that sine squared x could be sine squared x squared plus cos squared x all squared. And then in reality, I've got an equivalent form of a squared minus b squared. So I get a minus b, a plus b. So sine squared minus cos squared, sine squared plus cos squared. Obviously, sine squared plus cos squared is 1. So I get left with sine squared x minus cos squared x. Equally valid, you might have decided to change cos squared x into 1 minus sine squared x. And if you do that, you'll find that the sine to the power of 4 will cancel and get left with a 1. What do you get left with? 1 plus, or actually cos squared, 2 cos squared x, 1 minus 2 cos squared x, I think it is. And or you could have changed sine squared x as 1 minus cos squared x. Okay, so there's a couple of ways you could approach that and come up with equivalent expressions, which you'll see when we get to our double angle formula, that they're a similar expression for sine squared minus cos squared. For D, thought the simplest way was to split the fraction. Cos x on cos x is 1, cos cubed on cos is cos squared, so I get 1 minus cos squared, which of course is sine squared. Finally, for the proof, if we expand both sides of our equation, I get a sine squared plus 2 sine theta cos theta plus cos squared. On the second bracket, if I get a sine squared minus 2 sine theta cos theta plus cos squared, so my 2 sine theta cos theta plus 2 sine theta cos theta is going to cancel, and then I get 2 lots of sine squared plus cos squared, which are 1 in isolation, but together they add up to 2, which is what the right-hand side had to be. So we've done what we needed to.